Good morning. How are we doing this morning? Good. I like today's lecture. One of the reasons I like this lecture is that it basically sort of tells you a little bit more about a principle that you may have used in other courses. Things where, you know, you sort of learn something once and then you get to use it a whole bunch of different times. That's the kind of stuff I really like because it means you don't have to memorize as many things, right? And this is definitely in that category, the idea of superposition, okay? This is what it actually says on Wikipedia about superposition, and it's a pretty good definition, so I pulled it off of there to use it. It says the superposition principle, or also known as the superposition property, states that for all linear systems, the net response caused by two or more stimuli is the sum of the responses that would have been caused by each stimulus individually. So that if input A produces response X and input B produces response Y, then an input of A plus B would produce a response of X plus Y. Okay? Now that's, and it kind of needs to be, but this is very general, right? This is very abstract, what it's trying to get you to understand right here. But this principle is useful in many, many, many different applications. So I figured I'd start by just asking you, where have you seen this concept before? Where, okay, some people are responding in circuits. Okay, yeah, maybe you've seen this idea before in circuits. Where else? In what? Series. Okay. Maybe. I'm not. Okay, resistors in series. Okay, so that would maybe be a linear system, something like that. Thermo, tell me about thermo. Okay, so maybe like a conservation of energy, you might have some applications here. Some of the ones that I think of, we definitely use the superposition principle when we are trying to figure out the overall deflection of a beam. And we've got several different formulas that are available to kind of describe the deflection of beams. You know, and we can kind of take these common loading cases and pull out of a table formulas that would give us loading or a kind of deflection of a beam for that particular loading. But we can use superposition then to sort of add together several of them and get a more complicated loading scenario other than one that's just naturally listed in the table. So I'll put down in here beams. Okay. Anything else you've seen this? I've got a couple more ideas if you don't have more, but anything else that comes to your mind? Statically indeterminate type problems often rely on there being some kind of linearity with the systems that are part of them. That's a good example. What else? I'm going to give you two that may not actually kind of pop into your mind immediately. Have you ever heard of the concept of partial pressures? All right. Basically the idea that you can figure out the overall pressure in a gas using things like ideal gas law, but you can figure out what that is based on a certain amount of pressure for one gas plus a certain amount of pressure for another gas, and so on and so forth in a volume that is, you know, that is contained of a certain number of gases. Yeah? Yes, this is another really good example. So anything that involves a wave, right? Anything like sound waves or light waves, anything that involves a wave, if you basically transmit two waves in the same media, right? You've got two waves, the net result of those two waves is essentially like adding together the effect that you would have from one wave and the effect that you would have from the other wave, and they essentially behave as though they remain somewhat independent, okay? So let me put these in here as well. Gas law, partial pressure, and then the idea of waves adding, okay? But there's a lot more than just this. I was trying to think of some things that you may have seen before where we use this idea of superposition. What I need to probably talk through, though, is what do we even mean by systems, right? Because we're using words in this definition of the superposition principle, things like systems and things like linear. We need to talk through what these actually mean, right? And so in order to do that, I am going to introduce you to kind of a whole language that is used to talk about how systems interact and different elements of a system interact with other elements in that system. And that technique that I'm going to introduce you to today is called block diagramming. okay? So you'll get to see kind of what that looks like. And then kind of the last thing I'll talk about is, well, how do we actually use this with respect to circuits analysis, okay? So that's where we're going today. Let me get into the concept of representing things with block diagrams. And I think the easiest way to kind of describe this is with respect to a system where we need to try to describe the behavior, right? And the one that came to my mind is a soldering iron. There's a bunch of these different kinds of things that might be out there, but you know, if you think about a soldering iron, that, you know, something like I'm showing over here, what is its basic job? To get hot, okay? Now, can it do that job better or not as well? Okay, what would be a bad job of getting hot? Being cold would be a bad job of getting hot, right? That's definitely true. What else is a bad job of being hot? Getting so hot that you're causing problems, right? You're hotter than you need to be for the job that you are doing. So there's a window of temperature that you would like your soldering iron to remain within, okay? And for the one that I'm showing you here, there's a way for you as the user to specify what kind of temperature you want at the tip, right? How do you do that on, you know, by the appearances at least of this picture that I'm showing you? How do you specify what temperature you want at the tip? With that little knob right there, right? So let me actually kind of abstract some of this and say, you as a user, you get to specify what angle this knob is at, right? Let's call that angle theta. That's your input into the system, right? You get to control that angle of that knob, right? Okay, and then what happens as a result of putting that knob somewhere? Okay, changes might happen to this temperature, and probably what it's going to try to do is get to some specified temperature based on the position of the knob, right? So let me call that, you know, over here, I'll just call this the temperature, the temperature of the tip of this soldering iron. So if we want to abstract the behavior of this soldering iron in a way that we can see how it might behave kind of in a bigger system, what we can do is we can make a block that is the soldering iron, right? And the way this sometimes works is you say soldering iron, this is the device, is the soldering iron, okay? You put that in a block, and you then identify what are the inputs and outputs of this block, right? And there can be multiple inputs, and for some blocks there's sometimes multiple outputs as well. For this one, based on what we've talked about, I'm basically talking about a system where there's one input and one output, right? And what's the input? A knob angle. Okay, I called that theta. And what's the output? Temperature. Okay. And that might be measured in some kind of temperature scale. I won't necessarily put it on there, but that can be a number, right? Like that is actually a quantitative value that I can think of coming out of there, correct? All right, here's what I want to show you. What we've done with that soldering iron is we've essentially kind of described it as a function, all right? Down here in the block, I say, think about the essence of a mathematical function. We usually think of a mathematical function being something like this, f of x, and then we have some kind of definition of that f of x. But think about the pieces of f of x, right? What is x? Yeah, x is like an input, someone says, similar to the theta that we have in the example that I'm showing you right here. So this is an input. And what is f doing? Okay, this is essentially an operation on the input, right? So operation on input. And the only reason that you usually have something kind of over here is to describe, hopefully somewhat mathematically, what that operation is that you are going to do on the input. Does that make sense? So what I want to kind of point out is that when we make block diagram representations of things, what we're really doing is showing graphically some kind of function, right? You got something that's taking an input, operating on that input in some way, and then producing an output. Okay? Now, it's possible for us to take a system like the soldering iron, and if we know a little bit about what's in there, you might even be able to deconstruct it, because I doubt very seriously that there is some kind of a physical thing that you can find that will directly take knob input and produce temperature, right? Like just one piece. That's all you have to do is just put the thing in a particular spot and you get a temperature on some part of the body, right? You actually have to set up some stuff inside of this system in order to make that happen, right? Let me kind of deconstruct it to at least one layer below what we're talking about with just the big block, right? In other words, I can take this system and I can deconstruct it, and I can say, if I've got a particular knob angle, what that might feed into, I don't know, I haven't actually taken apart this specific soldering iron that I've got right here, but what it might feed into is a thing called a potentiometer. You know what a potentiometer does? Okay, it sounds like it measures something, right? It actually doesn't. A potentiometer is like a variable resistor, where it has a lead on both sides and it's got this little wiper that wipes across the terminals. And what it does is, if you put a voltage across the outside leads, how much voltage you will see on the wiper is going to be a function of where you position the knob. Okay? So basically what a potentiometer is, it's a device that takes an angle for the knob input, and what does it output? A voltage. So that's kind of a signal, if you will, that is coming out of the potentiometer. Now, who cares? We've now got a voltage coming out of a knob. How do I know whether or not the soldering iron is actually reaching the temperature that it's supposed to? Okay, well, you want to put that voltage to a resistor. Really what this is, though, this is a voltage signal that's proportional to how much temperature you want. But if you have a really, really heavy-duty heating element right here, there's some kind of relationship between what that heating element is doing and what it's doing as far as temperature goes. And so let me actually put that over here and say, let's say there's a heating element inside of here. Okay. How does the heating element know what to do? Based on how much voltage it gets. But the problem is, what happens if I stick this soldering iron, what if I stuck it into a very, very large amount of solder that is cold? What's going to happen to the tip? It'll start getting cold. What if I put it into some solder that's already hot? What might happen to it? It might get hotter than it needs to. So the way this thing probably works is that it probably has some kind of a sensor in the tip, right? So let's say what comes out of this heating element is a particular amount of temperature. What we might want to do is measure that temperature using some kind of a sensor. And maybe what will happen with that sensor is that it might be able to convert its signal into a voltage that I could compare against the voltage that I get from the knob angle through the potentiometer. And what that a lot of times does there is we can take what that desired temperature is as a signal coming from the potentiometer and subtract it or subtract off the signal that's coming from the sensor. And what that actually gives you coming into the heating element is sometimes called an error signal, right? Why is that useful? Basically, if your temperature is already the value you wanted based on the knob position, this is going to tell the heating element there's nothing for you to do, right? But if your temperature is lower than it needs to be, right, then what you'll get is a non-zero error signal that'll go into the heating element and say, hey, you might want to actually heat yourself up because your temperature is lower than it needed to be. Does that make sense? So one of the big benefits of using block diagramming like this is it makes it easy for us to sort of portray what are called feedback systems, right? Where you actually are measuring some result, feeding it back in, and then trying to control maybe what you are doing with a system, and it makes it easy for us to portray that kind of idea, okay? But at this point, the main thing I want to do is just kind of introduce the concept of block diagramming, and then what you're doing with each one of the blocks is you are essentially applying a function, right? It gets some kind of input, right? The heating element might have some kind of an error signal that it watches, and then it decides whether or not that heating element should be on depending on what that error signal is, right? And any one of these, right? The sensor, it probably has some kind of a transducer that's measuring temperature in the tip. It's taking that and converting it into some sort of voltage. It might need to also process that voltage somehow to make it suitable to compare with the potentiometer voltage. But once it does that, it creates that error signal. But any one of these pieces, I guess, my point is, each one of the pieces is acting like a function, and we can, you know, make a bigger system easy to represent based on looking at these little blocks. Okay? So that's kind of the idea behind using block diagrams. And then I guess the other thing I should probably really point out here is that in the definition that we had up here, we were talking about things like stimuli and responses, okay? Each one of our blocks has a stimulus and a response. How does that look for the overall block I did for the soldering iron? The stimulus is knob angle, the response is tip temperature, right? So, you know, this kind of gives us an idea of how these work, but even if we kind of break it down into smaller blocks down here, it still works that each of those blocks has a stimulus and a response. Okay? All right. Let me get on with, because I don't want to get bogged down with that too much. There are a couple of special kind of blocks, and one of them I just used on that last picture without really talking about it a whole lot, so let me talk about it now. A special type of block to put on a block diagram is called a summing node. Okay? Its job is to take two different signals and add them together and then create some kind of an output, right? It's going to add them together to create that output. Okay? And what those look like is a little circle like this, and depending on whether you are supposed to add the inputs together or whether you're supposed to subtract one of the inputs, what you'll see is that either a plus or a minus is going to be stuck inside the circle for a particular input. Okay? So that's how you read that on a diagram, is you're taking several different signals, adding them together to get an output, but if you see a negative, that means you're not adding, you're actually subtracting. Does that make sense for that? So right here, instead of saying input 1 plus input 2 plus input 3, what would I actually need to change in this string to make this accurate for what you see right here? You'd probably want to subtract that input 2, right? Because I put that negative sign as the input. Okay? So that's just kind of explaining how you would use a summing node. A gain is essentially just multiplying some signal by some constant. That's what a gain does, right? So whatever input you've got coming in, if you multiply it by some constant that here I'm calling k, the output is just going to be equal to that constant times the input. Okay? And remember that basically, generally with all of these things, what we're doing is we're representing functions, right? So we have basically an input, let's call it x, an input, let's call it y. What comes out of here? Some kind of a function that I might call f of x and y, right? That's what we're doing with any one of our blocks, is we're just representing a function. And each of these would be a special kind of function, right? In one case, the function is adding together your inputs, and in the other case, the function is to basically multiply by some constant value. That constant value, by the way, at least how I've set this thing up, is not a signal itself. It's sort of considered to be sort of hardwired into that, whatever that block is. With me? All right. So here's the, kind of let me show you how you can use block diagrams to represent things that we should be somewhat familiar with from this course even, right? Look at this block right here, or this, the circuit that I've got right here, where I've got a dependent source that is, got some factor of k times Vx, where Vx is the voltage across R1, and then I've got some current Ix that's feeding in here. The first thing I want you to see is that our inputs into our circuits problems, we usually represent those as independent sources, right? If you think about what's going on in a circuit, an independent source is this value that sort of comes out of nowhere, right? It's like, well, there's a source that's actually just generating that voltage or just generating that current, and you don't ask any questions about how or why, right? So when we're dealing with these kind of circuits problems, the independent sources are like our inputs, okay? So far so good on that. And then that feeds into this whole circuit, and what we want to define is Vx as the output, where Ix is the input, okay? And I want to see, can we represent that circuit as a block diagram? What do you think? I think we can, okay? So let me actually start by showing what the, I'm going to bring this down just a little bit here. Let me show Ix as an input coming in on the left. You don't always have to have an input coming in on the left, but that's sort of kind of the default way that people usually show a big system, is that you got some input coming in from the left. So let's call that Ix, okay? And then on the other end, we have some kind of an output. So let me call it, what is our output? Vx. All right, now, we have to like make some kind of a starting point with this. And one of the things that I would ask us to sort of look at is look at this node up here at the top. I have Ix coming in right here, right? That's what that current source is doing, is it's driving a current of Ix through there. And then let's say that I've got I1 is 1 volt, or 1 current, excuse me, that's flowing down through here. We call that I1. If I know I1, can I relate it to Vx? How do I relate it to Vx if I know I1? Ohm's law, what does Ohm's law say? Say, current times resistance gives you voltage, right? And so what I would actually propose is that if I put a block right here and call the operation that it does is just multiply by R1 basically, right? What do I have to feed in to get Vx? I1, right? Does I1 relate in some way to Ix? It does. We can think about Kirchhoff's current law if we want, and we can say, well, Ix, right, is sort of a combination of two different currents, right? Tell you what, because this might make this easier to put it this way, let me put it like this. I'm going to call that I2. What does Kirchhoff's current law say? Yes, sir. It does, because it doesn't matter, and you know, I could have done it either way. I actually have some notes up here, and I flipped it so that I stayed consistent with my notes. All right. It doesn't really matter which way you go. It might change a few things as far as how they look on the block diagram that we are doing, but at the end of the day, they'll end up being the same as each other. Okay. So I don't really care what direction it goes. I only flipped it just so that I'm kind of consistent with the way I worked it before. Okay. So I2 is going to go to the right like this. My question is there a way I can create an I1 signal assuming that I know Ix and I2? And how do I do that? Okay. Ix minus, if I can somehow get an I2 signal from somewhere, subtract it from Ix, what do I get? I get I1. So now my big problem is there a way I can describe what I2 is going to be, right? So far, I don't necessarily know what I2 is going to be, but let me kind of use a similar, I guess, method or try to do something similar to what I did last time. Does I2 relate to anything by Ohm's law? Okay. Okay, R2 allows us to relate I2 with another voltage that I don't even have labeled up here, but let me label it up here. What if I've got let me call it VR2. And I'll show it up there like that. Okay? What I can do there is I can say, well, I2, if I have VR2, if I divide by R2, that gives me I2, right? So if I put in here, let's say, 1 over R2, then what I have to feed in there to get I2 is VR2. Okay, so far so good? All right, now, is there any way for me to figure out what VR2 has to be? Okay, someone says KVL. So let me actually kind of flesh that out a little bit. Look at this loop right here. Right? That loop says that if I have minus K Vx plus VR2, then what? Plus Vx, that has to be equal to 0. I can take that and I can solve it for VR2, right? What do I have? KVx minus Vx. Is there a way I can get that off of my Vx signal that I have over here? I could, or I could just do two different paths, right? One of the things I could do is I could just take Vx all by itself, right, and actually subtract it. But then what else do I need to do? I need to add K times Vx. How do I do that? Well, I can use a gain. Add those together, what do I get out? VR2, which I can then feed into 1 over R2 over here. And I just noticed just now that I probably should have written an equation like this whenever I did my KCL, because you know, y'all didn't keep me honest on this. Okay, for KCL, for this summing node right at the beginning, what should that have looked like? Okay, what you would have there is if you sum your currents leaving the node, you would have minus I1, plus I1 leaving the node, right? Minus I2 minus Ix would be equal to 0. And if what we're trying to do is solve for I1, what would that be? I2 plus Ix, right? So how is my diagram that I have shown right now incorrect? I shouldn't have subtracted that. That should have been added right there, right? Okay. This is a block diagram representation of how that circuit behaves. Isn't that interesting? It might be more complicated, but the thing is about this representation of it is that if you can identify how each of the elements interacts with the other elements, it is often possible to take your block diagram and reduce it down mathematically once you have expressed it, and it's a lot of times not that difficult to do that. Okay, so I'm not actually saying there's that much advantage to doing this. More or less, my goal with showing you this little problem is to kind of get you to see how block diagrams work, right? That's more or less my goal. It's not so much that you're going to be solving a bunch of problems in this course using this method. Okay, and I do have a kind of a bigger goal out of all of this as well, but it takes me a little bit of scaffolding to get there, so thank you for your patience. All right. One of the things that it says way back in our very beginning where we said the superposition principle says that for all linear systems, the net response caused by blah, 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 right? It takes a little bit of effort for us to define what we mean by linear systems. And basically, they are systems that satisfy two criteria that each have names. One of them is called the additivity property, and the other one is called the homogeneity property. And so what I'm going to do now is go through those two properties and kind of describe what they mean. Okay? Here's the first of the two, right? The additivity property. Let's say that we have two options about how you are going to take input signals and make an output signal. Okay? The first option is you take your two input signals and you add them together right away. Okay, so let's say you've got input signal 1, you add it to input signal 2. Okay, then you feed whatever that result is into your system, okay, your block or whatever. I'm going to call this, since I use this terminology in my descriptions over here, I'm going to call this the given block. Okay, and then you get an output out of that given block. Okay, let's say you have this option for how to connect it up, or your second option is, let's say that you've got your two inputs and you are going to feed each of them into its own given block. So the reason I name these the same thing is I'm saying, let's say that you could replicate whatever that physical thing is so that you have two things here that both act the same exact way under the same inputs, right? So imagine, you know, this, if you're talking about a soldering iron, you now have two soldering irons that you put one signal from one knob and then another signal from the other knob, each going into its own block. Does that make sense? But the block in these cases behaves the same way as the block that I have up there in that case, right? Once you've done this, you take the outputs of each of these and you add them together in order to get an overall output. Okay, so this is the second strategy on how you could combine these two signals together. The additivity property says that if your system doesn't care which of these two ways you do it, that for any inputs you give it, you'll get the same output in either case, right? Then your system satisfies the additivity property. All right? Basically says it doesn't matter whether you add the inputs together first before you apply the particular block, or whether you apply the block to each of the inputs and then add that result together to get a final result. If it doesn't matter which of those two you do, you'll always get the same result out of the output. Then your system satisfies the thing called the additivity property. Okay? Because I want to not let this stray too far away from circuits, I decided to give you a quick kind of sample of this. Okay? Let's say you've got a system being a resistor. Now that resistor can accept an input of I1 from a current source. And let's say that we're saying that the output of that system that is just the resistor is the voltage across the resistor. Okay? So we could actually say in case 1 what that V out 1 was. What is it going to be? I1R. Right? Easy. Let's say I then take a second input and I call it I2. Right? What's V out 2 going to be? It'll be equal to I2 times R. What is the sum of those two outputs? This is just going to be equal to I1R plus I2R. Or if I want to, I can factor out the R and do what? All right. Now, let's say I go over here to my other case that I'm dealing with over here where I've got my two, I1 and I2. I've got those two values that I am putting together in parallel based on source, ideal source combination. How much current flows here? I1 plus I2, right? So that would be like, as far as the resistor knows, that's what it's getting, is this I1 plus I2, right? So that I1 plus I2 is flowing into the resistor. What is V out going to be? Okay, it'll be whatever that current is, which is I1 plus I2, multiplied by R. Or I could write it this way, R times I1 plus I2. Does it look like the resistor satisfies the additivity property? Okay, it does, because I applied the two currents individually, right? And I came up with this as the result as far as the voltage that you're going to have if you were to take one input and put it across the resistor and then add that result to the other current, putting that across the resistor. Adding those two results gives you R times I1 plus I2, which is the same thing that you get if you add them together first and then feed them through the resistor. That makes sense? So this is functionally, one example of kind of what we're doing with the superposition principle in circuits. Okay? All right, but this is the additivity property. We have one other property that we want to deal with, and it's called the homogeneity property. So let me show you what that one says. Okay? This one says, suppose you have two options about how you can take an input signal and make an output signal. The first of the two says you could apply a gain to your input signal first. Okay? So what that would look like here is that you'd put this gain, say a value of k or something like that, and then that would feed out into, here I'm calling this the given block again, right? And then I create an output based on what that chain of things are that I'm doing right there. Okay? Let's say that my other option is that I, instead of applying the gain first, let's say that my other option is that I could first put the input into the given block, and then after that, I could go ahead and apply that gain. Okay? The homogeneity property says that if you get the same output for, regardless of which of these two ways that you do it, if you get the same output regardless of the input, like if you give each of them the same input, you'll get the same output from both of them regardless of what that input is, right? Then that means that the given block there satisfies what's called the homogeneity property. Okay? And so I'm going to give you an example of this one as well. Okay? The way I'm going to give you this example is by showing you a few different blocks, but I'm kind of show them as circuits, but imagine you could hook these things up in different orientations, right? So I've got one chain of these little blocks right here that has an input signal, and then a gain circuit, and then a voltage divider. For the gain circuit, what it's doing is it's watching what voltage comes in on this terminal. It doesn't need any current to flow or anything like that. It's just watching what that voltage is on that terminal, and what's it doing? It's applying a variable or a dependent voltage source so that it produces some other voltage out of the output terminal, right? So that's what this is doing, is it's essentially applying a gain to my Vx, multiplying it by k for the output, right? What about this one? What's it doing? Well, it's taking whatever you feed into the input terminals and running it through this thing that's called a voltage divider, and then we get some kind of a voltage on the output over there after it does that, okay? So let me actually copy this, since I'm going to show you two different options about how to do it. So let me get a fresh copy for the two different ways here, all right? Now, the first way that I want to show you how this might work is exactly in the order that it's already shown, right? So let me do that by taking this block basically and saying I'm going to hook that up to my input, right? Then I'm going to take my voltage divider and hook that up, right, like this. And the output that I'm trying to identify here is, what is this voltage output? I'll call it V out over here. But it's what's that voltage that we get on those output terminals. Okay? Based on this first way of connecting it, how do we determine what that would be? Let me call this first V1. Or that was V1 over there. Let me call this maybe VA. Got to use different variables, right? Different letters. What is VA going to be? VA is just going to be equal to K times V1, right? If I put VA now across this voltage divider, what do I get for V out? Okay, a voltage divider works by voltage division, right? And what you'll get is just VA times what? R1 over R1 plus R2 would be V out. Agree with that? Okay, so I can do a little substitution here and say that V out then is just going to be equal to KV1 times R1 over R1 plus R2. All right. That may not have surprised anyone that that came out that way. Let me show you what other way we could take this same setup and hook it up. What if I take, and instead of putting my input signal directly into the gain circuit, I put my gain circuit to where the output of the voltage divider goes into that gain circuit. Then we're going to take that whole circuit and we're going to try to move it to where the input, the input signal is attached immediately over here to the voltage divider, right? And I'm going to define the same kind of output voltage over here, V out. Okay? Let me call this over here VB. Okay? What's VB going to be for this circuit? Okay? So VB is going to be equal to V1, right, times, I think what you said was R1 over R1 plus R2, based on voltage division formula, right? Now, the gain circuit over here, its job is to make V out be equal to K times VB, because VB is what we're feeding in to the gain circuit, right? Well, I can now do a substitution on this and say V out is just equal to K times VB, which is V1 times R1 over R1 plus R2. Does that look familiar? Those end up being the same, right? So I would say that the voltage divider, which is my given block in this particular example, is an example of being something that satisfies the homogeneity property. So it doesn't matter whether you apply the gain before you go into the voltage divider or whether you apply the gain after you go into the voltage divider. So see how that works? Okay. All right, so these are the two big properties that define whether or not you have a linear system, and when you have a linear system, you can use the superposition principle. Let me show you one of the reasons, probably one of the big reasons at least, why I wanted to show you all this stuff with block diagrams. It's because one of my favorite things that I have seen to describe sort of linear systems and how we can know whether or not superposition is going to work is this diagram right here. Okay? What this diagram shows is two different options on how you can apply some transformations to two input signals. Let's say that's one input signal is X1. This is another input signal, it's X2. Okay? In one case, we're going to peel off the signal, right, and apply some gain to it in each of these cases, right? So there's going to be two different gains applied to the two different signals. That gives you a gain applied to that input signal that you then add together. By the way, on these summing nodes, sometimes they put a little X through it and sometimes they don't. It doesn't really mean anything other than just to show you the different stations of where you can do inputs on a summing node. So don't let that throw you off that there's a big X through the middle of this summing node. Okay? What we're doing is we're going to sum the gains applied to each of those input terminals, or input signals, and then we're going to see that you get the sum coming out of here that if you apply to the system, you get this output that they're calling Y3 of t, right? The other path that you could take this is you could immediately apply the input signal into the system itself, which will result in two different kind of results of those are functions, right, that are being applied to the input signals. So you get these outputs that if you apply those gains, you end up with that signal over there. If you have a linear system, then these two signals will always be the same, regardless of what your inputs are. Does that make sense? This is the application of homogeneity and additivity put together into one thing, describing this is how linear systems will work. It's that those two outputs, whether you do it one way or whether you do it the other way, right, it gives you the same result. Okay? Now, I'm going to show you an example here of how we can use this with a circuit, and then I'm going to come back to this idea when I'm done with that example. Does that sound good? This is practically what it means when we start getting ready to try to work a circuits problem using a superposition method. Okay? And I'm kind of broken this down into steps so that you can see exactly what we're trying to do. Okay? So this is the circuit we're going to analyze over here on the left. It says use the superposition method to find the voltage labeled Vx in that circuit. Okay? Step one is we want to turn off all independent sources, right? Independent sources represent sort of inputs into a system, right? And so what we do first is we think about turning off all of those independent sources, okay? Turning off a voltage source means 0 voltage across the terminals of the voltage source. What's the easiest way to ensure that you have the same voltage on the two ends of a voltage source? Make it a wire, right? A wire's job is to try to have 0 voltage anywhere that, across any two positions of that wire. You're assuming the wire is a resistance-free wire, right? So that's where I say here, voltage sources become like short circuits. You replace them with essentially a little wire jumper, right? Current sources, what we're doing when we turn those off is we're trying to make those 0. Okay? What's the best way you can assure you have 0 current flowing from one lead to another? Infinite resistance, or you can think of it as being literally no path for the current to be able to flow, right? So you have an open circuit in the case of current sources to essentially turn them off. Okay? So with step one, what you would want to do with this little circuit that I've got drawn over here is you might want to copy it and then apply that change that I just represented right there, right? We're going to turn off all of the sources, all of the independent sources. Okay? So what happens with the current source over here? I can basically just do that. I can erase it, leave open terminals right there, no path for current to go across those two little terminals that I have right there. So that has turned off the current source. What about the 24-volt source up here? You just replace it with a wire, right? Straight up, connect right across like that. How do I turn off the 8-volt independent source? Another wire, right? So that takes care of those sources. And at this point, one of the mistakes a lot of people will make is they forget to read carefully that this says independent sources. What do you do with dependent sources? Nothing. You leave them alone, right? So we are done with step one. We've turned off all of our independent sources for that circuit. Okay? So what we did right there, I'll just label it. This is step one. All right? Step two says, turn on just one of the independent sources and evaluate the quantity of interest. Okay, so I'm going to take this circuit and copy it again. And I can pick which one I want to do. Which one of these sources do you want to deal with first? Okay, we can start with the 24 volt, that's fine. So what we'll do is we'll basically go back in and show it there again, right? So that 24 volt source in the original circuit was oriented like this. And it says, and evaluate the quantity of interest. I'm not sure if I've used that phrase in here yet. What do you think that means when I use that phrase, quantity of interest? Okay. Find what you're looking for. That's the, kind of the vernacular on it. Basically, usually what you get that from, at least in the context of like engineering problems, it's what's the problem asking for, right? That's your quantity of interest. So up here it says, find the voltage labeled Vx, right? So that is my quantity of interest, right, is the voltage labeled Vx. All right? So how do I find that for this, version of the circuit that I have just shown right here? I'm going to call this step 2A. How do I find Vx for this circuit? Okay, now some of you are probably getting a little scared because you see that dependent source over there. Dependent sources are very scary. Okay? Is that you? Well, don't be scared. Let me ask you this. Do we have a variable that gives us current everywhere in this circuit? In other words, is this just a single loop circuit, right? There's only one complete path for current to flow on, right? And we've labeled it IY, right? Now, let me ask you this, because I want you to see this. If I know that IY flows kind of through this voltage source that direction and comes down right here, what if instead of having a dependent source right here, I had a 10 ohm resistor? How much voltage would you see across the 10 ohm resistor if this was a 10 ohm resistor instead of this dependent source? You'd have 10 ohms times IY. What do I have for the dependent source? 10 ohms times IY. Turns out that at least for this scenario right here, this dependent source is not different than just a 10 ohm resistor. See that? Because you're going to have IY that's flowing down through here. The voltage across here is going to be 10 ohms times IY, which is the same as you would have if that was just a 10 ohm resistor. Okay? So let me go ahead and say this is equivalent to if this was just a 10 ohm resistor. All right? Now that that's just a 10 ohm resistor, how do I find Vx? There's a really nice clean formula that I've shown you in here that might be useful here. Voltage division, right? Vx, I'm going to use another subscript on here. This is Vx sub 24. Why am I putting that subscript on there? This is the contribution of the 24 volt source to the overall Vx that I will have for this system, right? And it's just going to be equal to 24 volts times what? 10 ohms being the resistor across which that Vx, is seen, over the sum of 10 ohms plus 10 ohms for the other resistor over there on the left side plus 20 ohms. Now I'll tell you what I'm going to do. I could easily evaluate what that number is, but I'm not going to do it. I'm going to leave it like this for now. Okay? You'll see the method to my madness here in just a minute. All right, so we basically did step 1 and the first time through step 2. What does step 3 say? Repeat steps 1 and 2, turning on a different independent source each time until the contributions from every independent source are all known. Okay? So I probably need to go to something like step 2b, right? Because I've already done step 1. I can go back and think of what this is going to look like with no sources in there. Step 2b says I'm going to pick a different independent source and turn it back on. Which one do you want to do next? Okay, you want to do the 8 volt source next. I'll do that next. Okay, so I'll take the step 1 version of the circuit. I'm going to copy it, and I will put that right here. Now what do I have to do to change this so that I've got the right circuit to analyze? That 8 volt needs to go back in there again in the same way that it was in the original circuit, right? Where up there it was negative to the left and positive to the right. Now, is anything different with respect to this dependent source over here? Or is it kind of work the same way as it did last time? Works the same way. So that really isn't different than a resistor that has a value of 10 ohms. Okay? So with step 2b, what is going to be Vx that the 8 volt source contributes? 8 volts times 10 ohms over the sum of 10 ohms plus 10 ohms plus 20 ohms. Now I do have to issue a word of caution before we say we're done with that equation we wrote right there. What word of caution do you think I'm about to say? Watch your polarity. Okay? Look at what direction this 8 volt source is going to want to drive current around this loop. What direction does it want to drive current? Opposite the way that you would have polarity for Vx the way it's shown, right? Like the 8 volt wants to basically drive current to go up around this way, which would make the positive side of voltage be on the bottom of that 10 ohm resistor, not on the top. Okay? So I have to be careful here because I'm trying to evaluate all of these with respect to the polarity that was actually given question, I'm trying to be consistent with that polarity, it means that I have to include a negative sign when I'm doing this contribution. That make sense? All right, so that's step 2B. Are we done? Probably not quite yet, right? What is the last of our independent sources that I need to get in there? Okay, the current source, the 4 amp current source over there. So I'm going to again take my step 1 circuit that I drew and copy it down here. Okay, I'm going to call this step 2C. Now I'm going to leave the 2 voltage sources off, meaning they're connected, right, with wires. And what am I adding back in here again? That current source, which I believe was 4 amps up, right? Make sure we're consistent with what it was up there at the beginning, 4 amps upward, okay? All right, so, and then I've got this, you know, this 10 ohms times IY, where IY is shown up here. Is it still valid for me to replace that with a resistor? Yeah, still will behave exactly the same way as though it was a resistor. Right? So that's a 10 ohm resistor over there. Now, what do I have that I can use to easily figure out Vx in this scenario? Well, how about this? There may not be something that's quite as direct as the last ones that we did, but the last ones we were using voltage division. In this case, we have a current. I would argue that that current flows right here. Regardless of what the, you know, we got that 50 ohm resistor right there, but it doesn't matter what the value is of that 50 ohm resistor, we're still going to have 4 amps flowing through it because that's what the current source does, right? So I have 4 amps that flows into this node up here, right? What does it do from there? It divides into 2 possible paths, right? Do we have a formula that might be useful for that? We do. Current division, right? What does current division say? Let me define this right here. Let me call this, since I called that Vx, let me call this current right here Ix. So what is Ix going to be? Okay, 4 amps multiplied by 10 ohms being the 10 ohms that I actually have over here, right? Because you're taking the path that's opposite of the one that you're actually trying to find, right? So I'm going to take 10 ohms over. Now what do I put in the denominator? I will use that 10 ohms again, but then the other path has how much resistance? 10 ohms plus 20 ohms, right? And just to kind of be clear here, the 10 ohms that I'm putting there and there comes from the 10 ohms that I've got on that left side, and then the other one, right, that 10 ohms comes from the 10 ohms that I have on this leg. Okay, well, yeah, so good question. Why? So I found Ix, that's how much current flows down through that leg. Why is that useful? Yeah, Ohm's law allows me to make a relationship between the current flowing down through this leg and Vx, right? What does Vx have to be once I know Ix? Yep, Vx is just equal to Ix times 10 ohms, or Ix is 4 amps, right? So we have 4 amps times 10 ohms over 10 ohms plus 10 ohms plus 20 ohms. All of that multiplied by what? 10 ohms again. And I wasn't super consistent here about how I labeled my Vx when I started this. What might be a good additional subscript to put on there? Yeah, something like, 4 amp to indicate that that is the contribution of the 4 amp current source. Same for Ix, right? That's not an overall Ix value. This is just the Ix that I'm going to have with just the current source connected. Okay? Now, have I gone through all of my independent sources? Yeah, I've done this for every single one of them. That means I'm done with step 3, right? We repeated steps 1 and 2, turning on a different independent source for each time the contributions, right, until they're all known. Then what? I add together all these pieces that I've got in order to get my overall Vx. So Vx is just going to be equal to Vx24 plus Vx8 plus Vx, called it 4a over there, I'll just repeat it again. So what is this going to be? 24 volt times 10 ohms over, I'll collapse that, I don't need to keep it like that, I'll collapse that down into 40 ohms, right? Plus what? Well, minus, I'll say, minus 8 volts times what? 10 ohms over 40 ohms plus 4 amps times what? 10 ohms squared over 40 ohms. And if you evaluate that, what you will have for the first entry there is basically 24 divided by 4, right? What would that be? 6 volts. Here I've got 8 volts divided by 4, minus 2 volts, right? And then here I've got, well, it gives you 10 amps at the end of calculating that whole thing. So what's Vx? Excuse me, thank you. 10 volts. Why can't it be amps? Yeah, so we basically have amps. Here we've got one of these ohms canceling out the other ohms, and I have amps times ohms is what I'm left with, right? That's volts. Plus, I better not be adding amps to volts directly, right? So, good catch. What does this whole thing add up to? 14 volts. All right. Now, here's the thing I told you I was going to come back to from this figure up here. There's a little bit of a, you can kind of see the flavor actually in this representation of how this thing will come out, that your inputs more or less can stay distinct from one another when you have a linear system. In other words, you're not going to have mixing together of all of your different inputs. You can essentially have mathematically separable inputs and what their effects are going to be on the overall system. Okay? I'm going to show you how that worked out with this problem down here. You'll notice here that what this essentially boiled down to was my 24 volt, my 8 volt, and my 4 amp. Those were all my inputs. But I could easily write this thing that would say my output, I'm going to generalize it to this, my output, which was my Vx, was equal to input 1, which that was 24 volts, times some factor, plus input 2 times some factor, plus input 3 times some factor. And if I had had more independent sources in this problem, it would have worked the same way. I could have just kept on adding terms into this function. Now, what happens if I change one of those inputs? It will only change the output based on how that input changes that one term. But you know what doesn't change if you change your inputs? Factors 1, 2, and 3 don't change when you change your inputs. So this is something that actually makes superposition fairly powerful because it allows you to do sort of some what ifs, right? You can say, well, what would happen if I changed my 8 volt to where it was 16 volt instead? What's the only thing that has to change in this process? The only spot you have to change something is that value right there. The rest of the circuit will work the same way. You can just plug in a 16 volt there instead. That, easy enough to do it, right? That would just make this 4 volts. You'd have your final answer being 12 volts if you change that 8 volt to a 16. That make sense? Pretty powerful stuff, okay? And so I think that's about where I'll leave it. Any questions before we get to our assignment we're going to work in here? Fantastic. Let's get to it.